stapling and stuff after we're done. So there are many examples of growth. You can, page 19, it's page 19. There are many examples of growth in the real world that occur at a constant percentage rate, and that's what we're talking about. So you have a population of fruit flies that's growing at a constant rate. It's growing at a constant rate of 6% per hour. So that means if it's growing at a constant rate of 6% per hour, that means that we're going to take to find the B value, we're going to take 1 plus the rate. So we have to turn 6% to a decimal. That's the first thing that we need to do. So what is 6% as a decimal? What's 6 divided by 100? Or take the decimal and move it 2 places to the left. 0.06. Okay. So that's our rate. 1.06, because 1 plus 0.06 is 1.06. It says that the population starts when time is 0 with how many flies? How many are we starting with? What's our initial value? 28. That's A. So your function y equals 28 parenthesis 1.06 to the power of t. That's the exponential function for this. That's the exponential function for this. Let's talk about how to represent this using repeated multiplication, because that kind of is a weird question, and you have something like this in Delta Math on Monday. So we started with 28, and each time we're going to multiply by 1.06. So if I say t is to the power of 1, how many times am I multiplying by 1.06? So that's my exponent. Just one time, right? If my exponent is a 2, how many times am I multiplying by 1.06? 2 times. 1.06 times 1.06, right? Because that's 1.06 to the power of 2. If t is 3, if the time is 3 hours, how many times am I multiplying by 1.06? 3, yeah. You do have one question like this in Delta Math that asks you to show it as repeated multiplication. So that's what it's asking you for. So what is the value of P of 24? What's the value when I let T equal 24? When the time is 24 hours? How are we going to figure this out? Well, can't we take our function y equals 28 times 1.06 to the power of 24? So you can either put that in your y equals and go to the table and find out what happens when x is 24, or you can just put this part into your calculator on the front screen, right? You can just do that math in your calculator on the front screen. What does it give you? Yeah, it's about 113.37, and I don't think that we want 0.37 of a fruit fly. So we're going to say there's about 113 fruit flies after 24 hours. There's about 113 fruit flies after 24 hours. So it says, what does the calculation that you made in C represent about the fly population? Well, it's growing rapidly. What is the range when I let my domain values, when I let my x values equal 0 and 24? Well, when the time was 0, when I first started, how many flies did I have? When this first began, I had 28 to start with. And after 24 hours, I had 113. So the range is between 0 and 113. It's not asking you for average rate of change or anything. It's just saying, what are the y values? What are the y values going to fall in between? Oh, not 0. Sorry. Not 0. 28. We began at 28. My bad. 28 and 113. So often we get to graphs, like when I check your homework, you guys always leave the graphs blank. And I'm not sure why. I feel like you think that you can't graph something. So I need you to just be real comfortable with your calculator and with Desmos, because you have Desmos at home, right? You can access Desmos at home. If you go to the y equals and you take 28 times 1.06 to the power of x and go to the table, we only need to find out what happens when x is 0, when x is 6, when x is 12, when x is 18, and when x is 24. That's plenty of points to give us a nice curve, right? Those are the big numbers on your graph. Those are the big x values on your graph. So plot that into your y equals, put that equation into your y equals, and then hit second graph. Hit second graph. And tell me what you get. So we know that when x is 0, y is what? 28. What about when x is 6? Yeah, when x is 6. It's not 200. 39.7. Okay. What about when x is 12? 56.3. What about when x is 18? 79 point what? 79.9. And 24, we said, was about 113. So we're going to just graph these. When x is 0, I'm at 28. Well, that's right below the 30, so I'm plotting that point right here. When x is 6, I'm at 39.7, so that's almost a 40. That's where I'm going to plot it. When x is 12, I'm at 56, so that's a little bit below the 60. When x is 18, I'm at 79.9, which is very close to 80. And when x is 24, I'm at 113. So your graph, my 28 disappeared. Your graph is going to look something like that. Your graph is going to look something like that. You need to feel comfortable using your calculator or Desmos to input these equations, and then you just plot some points to make your graph. Leaving them blank is not helping you, right? Leaving them blank is not going to help you pass a test. Okay, second question, number 6. Someone read that while I get out the filled out notes. Someone read number 6 for me, please. Please.
Get the saving from the account being modeled by the function s t equals 250 1.045 to the power of t, which is the following statement.
Okay, so savings account, S of t over time, 250 times 1.045. Is it growing or is it decaying? It's growing. How do you know? Because b is bigger than 1. It's growth. What's the initial value? How much money did I start my savings account with? I started with $250. Which answer choice says that I'm starting my savings account with $250? 1 and 3. So cross off 2 and 4 right now. Cross off 2 and 4 right now. They make no sense. Okay? So we know that it's not 2 and it's not 4. All right, so let's look at this 1.045 and let's subtract 1 from that and figure out the percent of growth. Well, 1.045 minus 1 is 0.045. And when I take that and I multiply it by 100, I find out that my savings account is growing at a rate of 4.5%. So is it answer choice A or answer choice, sorry, not A. Is it answer choice 1 or 3? 3. That's how you look at a function and kind of decipher it. Okay. All right, on the back, same exact thing. We're given a function. We have to write the equation for it. So a pool is draining water. We're draining water out of a pool. The depth of the water is decreasing at a constant percentage rate of 20% per hour. So if it's decreasing, am I going to add the rate to the number 1 or am I going to subtract it? When I do decay, do I add or subtract? You subtract. So let's see. I'm going to take, to find my B value, I'm going to take 1 minus. How do I write 20% as a decimal? 0.2. So what is 1 minus 0.2? 0.8. Okay. The depth of the water when the draining begins is 12 feet. What is this? When the draining begins, it's 12 feet. What does that represent? Initial value. So D, the depth of the pool, equals 12. That's my A value, times 0.8 to the power of T. 0.8 to the power of T. Okay. So you guys are going to use that equation and you're going to put it into Desmos. You're going to put it into, not Desmos, sorry, put it into your calculator under your Y equals. We want to get some points. So Y equals 12 times 0.8 to the power of T. So power of X, just use X. Sorry, honey, just use X. Yep. Good question. Go to your table. Go to your table. So the numbers that I'm looking for, I want to know what happens when X is 0, when X is 5, when X is 10, when X is 15, and when X is 20, because those are the giant numbers on my graph, right? Those are the X values on my graph. Notice that my Y value on my graph doesn't have any numbers on it. Why is that? Well, they want us to think about it. What's the starting value? How much water is in the pool when we begin? 12 feet, right? So at the very top, start at 12. And then I broke it in half and I put a 6 there. And then I tried to break that into so 2, 4 little increments, and then 2 more increments, 8, 10. That's kind of how I tried to do it on my notes. I don't have a working stylus, so it's a little sloppy. Okay, God bless you. So when X is 0, how much water do we have? Yeah, we have 12. That's where we're first starting. When X is 5, how much water do we have? Say it loud. I can't hear you. 3.9. Did it drain to 3.9 that fast? Did someone else get 3.9 at 5? Okay, keep going. When X is 10, how much is left? 1.2. When X is 15, how much is left? 0.4. When X is 20, how much is left? 0.1, what? Just 0.1? Okay, perfect. So we start at 12. When we go to 5, we're at 3.9. So I'm going to plot it right here at the 4. At 10, we drop all the way down to 1.2. So below the number 2. At 15, I'm at like point something. So this is going to go like this. Something like that, okay? That's what your graph looks like. Question D says it's not safe to cover the pool unless there's less than a foot of water. This is the type of question that I would put on a test. You can't cover the pool until you have less than a foot of water. So looking at your table, tell me when your Y value is less than 1, because that's how many hours we have to let it drain, for at least that long. Look at your table and tell me when your Y value is less than 1. Look at your table because it happens before 15 hours. Say that. Yeah, at 12 hours, because at 11 hours, I think at 11 hours, it's like what is it at 11 hours? 1.04, isn't it? Or something like that. Okay. So it's 1.03. That's not under 1 foot. So you have to let it drain for at least 12 hours to get under a foot. That's a good question because it's asking you to make sure that now it's asking you for the input. You have to look at the output and find the correct input. Does that make sense? It's the reverse of what you're doing typically.